Okay, good morning, everybody. Let's get started. Let's talk a little bit about the assignments, and then we'll jump back into lecture. Undergraduates, you're going to be tackling assignment 5 today. You're starting this week. So you have now implemented all the parts that make up a robot. So we're going to switch now in the assignments from working on robots to working on the evolutionary algorithm. So PyroSim has no evolutionary algorithm built into it. You are going to be building up a series of evolutionary algorithms, not unlike we did a couple weeks back when we talked about evolutionary algorithms, where you'll be starting with the simplest possible search method you can think of, which is random search. Super simple to implement, but incredibly weak and not ideal. Why not? What's the problem with random search?
It doesn't, when it detects improvement, it doesn't do anything.
It doesn't do anything with it even when it detects improvement. Yep.
The solution set is so large, or the possible robots, there's so many of them, so it's kind of hard to get a good one.
Exactly. So for most of the spaces we're going to be searching in the remaining assignments, the number of robots, to all intents and purposes, is infinite, right? So we got a hard task ahead of us. Random search doesn't work very well. We throw away good solutions, and often we get stuck in local optima. Remember our discussion about the fitness landscape, where every horizontal position in this potentially very high-dimensional space represents a candidate solution to our problem, which for our purposes is going to be a candidate robot, and the height of that robot is the fitness, how well it does at whatever we want the robot to do. Before we start implementing increasingly complex and increasingly powerful search methods, we're going to do a little bit of refactoring. So you're going to, at the end of part 1 of assignment 5 here, you're going to have code that does exactly what your code did at the end of assignment 4, but it's going to be cleaned up and it's going to be a little bit more modularized, which will make it easier for you to wrap increasingly complex search methods around your robot. So in refactoring, you're going to be creating a number of class instances and making your code object-oriented. For those of you that haven't done object-oriented programming in Python before you tackle assignment 5, this might be a good time to pause, go find an online tutorial about object-oriented programming in Python, work your way through that, then tackle the refactoring exercise. When you get towards the end of refactoring your code, you're going to have a class called uppercase robot, and whenever you call the constructor for that class, like here, you create an object instance which is stored in this variable called lowercase robot. So now we have an object called robot. If you call that constructor multiple times, you create multiple robots, and you can send more than one robot to a simulator, or potentially multiple robots to multiple simulators. So we're going to modularize things so it's relatively easy to create and destroy robots at your whim. Okay. In the case of the robot constructor here, we're sending it one argument, which is sim, the simulator that this robot is going to be sent to, and one additional argument, a value, and that value is going to represent the synaptic weight for the one synapse that exists in your robot so far. So remember our discussion about evolutionary algorithms where we separated genotype from phenotype. Genotype is the blueprint for the thing that we want to build, and the phenotype is the thing that we actually build. In this simple example here, the genotype, the blueprint, is one thing, one number, -1. That -1 is sent to the constructor, is sent to the robot, and labels the single synapse existing in that robot, and your robot now exists with all its objects, joints, motors and sensors, neurons, and its single labeled synapse. That's the phenotype of the robot. Genotype, pretty simple in this case, a single number. Later in the assignments, you're going to make your robot more complex. It's going to have more neurons and more synapses. So this single number is going to become a vector of numbers, and that vector is your genotype. That is the thing that your evolutionary algorithm acts upon. The vector sets the phenotype, the robot. We evaluate the robot in the simulator, and we get the fitness value back. Okay, just a little bit of orientation of where we're heading in the next few assignments. Any questions about that? No? Okay. Grad students, you are, if you haven't already, tackling assignments 9 and 10. There's a question this morning of what is life after the 10 assignments. Next week, for the grad students, I will talk briefly about the final project. Undergrads, we have a few more weeks until we have to cross that bridge. We'll talk about it next week. Any other questions about the assignments? No? Okay, so back to our history of evolutionary robotics. We worked our way through continuous time recurrent neural networks last time to prepare us for today's lecture on minimal cognition. Right at the beginning of the field, there were a series of experiments where the attempt was to try and make the robot as simple as possible, its task environment as simple as possible. The simple robot is equipped with a CTRNN, which is clearly not a minimal neural network. It's a little bit more complicated than some of the other neural networks you might have seen so far. However, generally speaking, we're going to look at some relatively simple experiments so far. We're going to simplify back or minimize the robot and task environment as much as we can, but not too far. We still want to be able to evolve these robots to exhibit the building blocks of intelligence. At the beginning of the semester, we saw how difficult it is to actually write down a definition of intelligence. This is an ongoing debate for the last 70 years. An easier thing to do is identify in organisms behaviors which we see as the building blocks for intelligence, and then see if we can take all of those different building blocks and instantiate them in machines. That was the goal of the initial minimal cognition experiments that we'll look at today. All right, before we look at those, let's jump back to lecture 8. We were just finishing our discussion on continuous time recurrent neural networks. Just as a little bit of a refresher, it's good to go back and look at this equation from time to time. It can be a little overwhelming to digest all at once. Just a little bit of a reminder that in the continuous time recurrent neural network, the values of the neurons are changing continuously over time, right? We have the value of the ith neuron, y sub I, and the little prime there reminds us that this equation describes the rate of change of the ith neuron that sits inside of a CTRNN made up of multiple neurons. If we have a 10 neuron CTRNN, we have a set of 10 differential equations. Each of the 10 looks like this. If we have a 100 neuron CTRNN, we have a set of 100 ordinary differential equations that look like this. All those equations have exactly the same form, but each individual ordinary differential equation might have slightly different values for tau, w, g, and theta. Right? You can see from the single subscripts underneath those parameters that those parameters are single or double subscripts. They're associated with the single neuron. Tau sub I is associated with the ith neuron and dictates the rate of change of y sub I. W sub ji is a reminder that that's the weight connecting the jth neuron to the ith neuron. The gain parameter, y sub j, is basically the volume of the jth neuron, how loud it tries to speak to all of the neurons that it connects to. Theta is sort of the default value of a neuron. Remember that because of this term here, a neuron value will tend to decay towards 0. By offsetting it right inside here with theta, when it decays, it will decay towards its theta value. Okay, let's play a little game here. Let's assume that we have a 10 neuron CTRNN, okay? And we're going to evolve that 10 neuron CTRNN. So we're going to place all the parameters of those 10 ordinary differential equations under evolutionary control. We're going to put them in one large data structure, which is the genotype. How many numbers, how many values are being evolved by that evolutionary algorithm if we're evolving parameters for a 10 neuron CTRNN? We're going to place all the taus, all the w's, all the g's, and all the thetas under evolutionary control. How many do we have?
40.
40?
130.
130. Let's start with W first. In a CTRNN, we're usually connecting every neuron to every other neuron. So if we have 10 neurons, we have 10 squared or 100 W's, right? We could store that in a 10 by 10 matrix. So we have at least 100 parameters under evolutionary control. In addition, we have the 10 tau values. So now we're at 110. We have 10 gain values, one for each of the 10 neurons. We're at 120. And finally, the 10 thetas, we're at 130. So to specify, to allow evolution to play with all of the parameters describing a 10 neuron CTRNN, we'd have 130 values for evolution to play with. All good? Okay, so back to the application of CTRNNs that we finished with last time. We were looking at this little guy here, this little humanoid robot. And in this case, unlike the example we just talked about, the researchers put all the W's, all the G's, and all the thetas under evolutionary control, but they set the tau values manually. They did not allow evolution to play with those. The reason why is they wanted to try and teach this robot or evolve a robot that was able to compose together motor primitives. Motor primitives are these simple things that we're capable of. For us, it's taking a step, writing a letter longhand, all of the sort of simple things you can sort of do without thinking about them. Once you learn how to take a step, or write the letter A or write the letter E, you can start to compose together motor primitives in arbitrary ways. You compose together stepping without falling over into walking without falling over. Once you learn how to write individual letters, you can then start to write words and paragraphs and essays and so on, right? One of the keys to intelligence is learning how to perform simple motor primitives and then being able to compose them together in arbitrary sequences. Hard to do with robots, as we saw last time, because in order to allow a robot to evolve and then perform 3 or 10 or 100 or 1,000 motor primitives, in the old days we would have a separate subnetwork for each of these motor primitives, and then use some additional gating mechanism that would allow any one of these subnetworks to take over the motor system when appropriate. It doesn't scale very well. Again, there's no good way to enumerate the number of motor primitives that we can perform, but it's a big number, and there probably isn't enough room in here for all of them to have their own small piece of neural real estate. So instead, what the researchers did in this case was to simply create two subnetworks. So they've got a mass of networks, they have a mass of neurons, and they cut some of the synapses. So now, not every neuron is connected to every other neuron, as you can see in this sort of messy diagram here. They have these two subnetworks here. Not all neurons are connected to every other one. In one of these piles of spaghetti, they set a tau value to 5, and in the other subnetwork, they set tau equal to 70. And if you can remember the CTRNN equation, the taus are on the denominator. So if you have a large number on the denominator, describing the rate of change of the neuron, that means the rate of change of that neuron is going to change relatively slowly. So these are our slowly changing neurons over here. And in the middle here are these fast changing neurons. And then finally, you can see on the left-hand side here, there's this third tangle of neurons. These are the input-output units, otherwise known to us as the sensor and motor neurons. So these are the sensor motor neurons that are getting information through the sensors from the world and then sending commands back out to the robot and causing it to move. These two clumps in here are masses of hidden neurons, right? Things that are not directly influencing or being influenced by the physical world. So far, so good. Question?
Did they design the neural network and, like, as they designed it, then set the taus, or how did they, like, designate which sections would have 5 and which sections would have 7?
That's a good question. So this is a bit of a complex experiment. So we're not going to touch too much on the evolutionary algorithm and how they actually train this robot. But as you can see, there's an interesting mixture here in which some of the aspects of the neural network they set by hand, and other aspects they're allowing evolution to play with. How did they come up with 5 and 70? That's hard to say. They probably played around with this a little bit until they got values that actually worked. Their intuition that was guiding them was this intuition down here. The intuition here is we're going to train the fast neurons to produce lift the block up and down 3 times, and train the same set of fast neurons to cause the robot to shake the block left and right 3 times. There are 3 different motor primitives here, represented by these 3 colored squiggles: left and right 3 times, up and down 3 times, and forward and back 3 times. Those are the 3 different motor primitives. We could train 3 different networks. They're going to try and train these fast units to produce any one of those 3 motor primitives when they're influenced in a particular way by the slower neurons. So a way to think about this, a good metaphor is an orchestra. You have everyone who's able to play their instrument, and then you have the conductor, and the conductor is producing some pattern which causes all the fast neurons or all the instruments to play a particular melody, and the conductor does his or her thing for a while, and then the conductor slowly changes to something else, and all the instruments change to a different melody. That's the basic idea here. The slow neurons are sort of slowly changing over time because they're slow neurons. And as they slowly change, they're changing their influence on the fast neurons, which push the fast neurons into one of 3 possible patterns: left and right 3 times, up and down 3 times, or forward and back 3 times. That's the intuition. In order to make that happen, they set some of these hidden neurons to change quickly and some to change slowly, and they snipped most of the connections between the fast and slow neurons. They snipped the synapses. Within the fast neurons and the slow neurons, there was complete connectivity using the W's. And then everything else, the values of the W's, the gains, the thetas, that was all placed under evolutionary control. And the fitness of any one of these C turn ends was how well the robot could obey the teacher. If the teacher said, grab the object, do left and right 3 times, then up and down 3 times, go, start again. Now grab the object, up and down 3 times, and then forward and back 3 times. So the teacher could ask for an arbitrary sequence of these motor primitives, and the robot could carry it out because the slow neurons would push the fast neurons into any one of these patterns. So far, so good? All right, how did the teacher tell the robot left and right 3 times, up and down 3 times, and so on? There's a goal signal coming in. You can think of this as sort of an additional sensor neuron. You can think of this as an ear, if you like. And when the teacher said, I want left and right 3 times, there was a particular value associated with that. It doesn't really matter what it is. We'll say it's -1. -1 means I want left and right 3 times. So as long as -1 was coming in, that would cause the slow neurons to do their thing, which would cause the fast neurons to do their thing, which would cause the robot to do its thing. Then the goal would change. It would change to up and down 3 times, and we'll assign an arbitrary value to that. Let's say goal equals 0. So the -1 changes to 0, which changes the conductor, the slow neurons, which change the fast neurons. And if this neural network is causing the robot to do the right thing, the robot will switch from left and right 3 times to up and down 3 times. While this is all going on, the robot is also receiving sensor data in the form of proprioception, which isn't mentioned here. Proprioception are joint sensors. They're telling the robot what is the angle of its arms and wrists and hands as the robot does its thing. So it's getting information, sensor information from its body, and it's also getting sensor information from the teacher. What does the teacher want me to do now? Again, this is a complex experiment. There's lots more going on here. For the graduate students, this is a good research paper that's worth sitting down with and working through the details. For the undergraduates, that's probably enough detail for our purposes today. Let's have a look at what actually happens. So what we're going to look at here is, as you can see, two columns here. And these two columns correspond to the teacher asking for two different sequences of motor primitives. In the first case, it might be hard to read here. The teacher asks the robot to shake the block up and down 3 times and then shake the block left and right 3 times. Finish. Go back to the starting condition. Then the teacher asks for back and forward 3 times. Stop. What we're looking at is how the robot responded to those two different sequences of motor primitive requests. And it's all one neural network. So we're assuming now that evolution has finished. We're taking the C tier and N that had highest fitness, dropping it back into the robot, and then we ask the robot to do these two different things. So far, so good? Okay. So up here at the top, we have, let's actually go down here. This is the teacher instructions. We won't worry about this. Let's look at this middle row here, which is the robot proprioception. So what you see in this particular panel here, we see 1, 2, 3, 4 curves, which represent the 4 proprioceptive sensors in the 2 shoulders and the 2 elbows. And as the robot moves, you can see those proprioceptive sensor values changing. Without seeing the video of the robot in action, did it succeed at the task? Did it shake the block up and down 3 times and left and right 3 times? Yes. We have the proprioceptive information here. There's also some visual sensors that we didn't talk about here. So the robot can actually also see the block moving in its environment. So assuming that this information represents the robot seeing the block, then the answer is yes. The robot feels its angles changing 3 times, and it sees the block moving up and down 3 times, and then left and right 3 times.
What line is what axis?
I don't know either. We'd have to go in and look at the details here about which is which shoulder and which elbow and so on. For our purposes, we can assume the robot is succeeding. It feels its angles changing, and it sees the position of the block changing 3 times. What you can't see from these 2 panels is whether it was shaking left and right or up and down. We'll assume for the moment that it is. So the robot is doing what we asked it to do. Let's now dive inside the brain of the robot and see what's going on while it successfully performs these actions. And again, I apologize, it's very hard to see here, especially from the back. We'll see this picture here, and we have 60 rows in this panel going from 101 to 160. Each row here corresponds to 1 neuron. And this panel here, maybe I can zoom in on it for you. That might help. There we go. Each row here corresponds to the value of that particular neuron. So the top row is reporting the values of the 101st neuron, and the bottom row is reporting the value of the 160th neuron. Where are the values for the first 100 neurons? They're not shown here. Those are the sensor motor neurons. So these 60 hidden neurons, as the name implies here, these are the fast neurons. And the 161st through 180th hidden neurons are the slow neurons. So we have a total of 80 hidden neurons in this case, and we can see how they're changing. Tell me about the conductor in the orchestra here. What's going on? Yes?
Well, in the slow neurons, the change seems to be more gradual. It's why they're more blurry, but
Yep.
it seems like there's a density shift in color. So in the first half, it's darker towards the lower neurons, but then it shifts towards the higher neurons to become darker.
Yep.
And then with the instruments, the rate of change is very fast, so it looks a little bit more pixelated, but there seems to be a pattern of 3 replicates, but they change very fast. You can see how they kind of are related and how the whole densities change.
Exactly, right? So you can sort of see the conductor and the orchestra metaphor here, right? We have more or less constant values in each of the individual hidden neurons here. That's not quite true. Some of them are slowly turning on and slowly turning off, but it's more or less constant over this period, which is the period during which the teacher was asking for up and down 3 times. So the goal was coming in, shake the block up and down 3 times. The slow neurons responded to that goal value, and they either turned off or turned on, depending on the weights and gains and thetas and so on. And as they were holding relatively constant values, that constant influence of the slow hidden neurons on the fast hidden neurons caused the fast hidden neurons not to hold constant values, but to oscillate 3 times. And obviously among these 60 fast hidden neurons, some were turning off while others were turning on, and vice versa. Right? Then, when the goal signal came in right around here, when the teacher asked no longer for shaking up and down, but now shaking left and right, that goal value changed from -1 to 0, and that changed the patterning, the activations of the hidden neurons. Here you can see a little bit of oscillation. So this metaphor of the conductor and the orchestra is sort of breaking down here. But generally speaking, the slow neurons are doing what you would expect. They're slow. Most of them are constant. Some of them are oscillating slowly. But among the fast hidden neurons, you can clearly see that there is a pattern that's repeated 3 times. Right? Most of the time in this class, thinking about thinking is misleading. This is one of the few exceptions where this kind of matches up with our own felt experience of cognition, right? When you leave the lecture today, you'll be thinking, head to my next class, head to my next class, head to my next class. Your high-level goal of what you're trying to do stays relatively constant until you get to your next class. And while you're holding that constant thought in your head, your legs are doing what they're supposed to be doing, right? They're oscillating, your arm is opening and closing doors. There's a lot of other details that are being filled in response to your high-level goal, which stays relatively unchanged until you get to your destination. Right? Okay. The nice thing about this, again, the original goal of this project was we don't want to just teach the robot left and right and up and down, forward and back, but it should be able to arbitrarily put these things together in different sequences. Same neural network. We're now going to ask it to shake the block back and forward 3 times. And now we get a different pattern. So this pattern differs from this pattern. So the neurons are doing something very different, and this pattern more or less differs from this pattern. So now, in the slow neurons, the robot is, quote unquote, thinking to itself forward and backward 3 times, and its arms are moving in a different way, or oscillating 3 times in a different way. It's composing these things together in different ways. Make sense? All right, so we spent a fair bit of time last time going through the nitty-gritty details of CTRNNs. They're more complicated than usual neural networks. So we want to be able to justify why we would bother implementing this more complex neural network. Here's one good reason why you might want to do so. One of the building blocks of intelligence is being able to think multiple thoughts at the same time. Your brain thinks, get to my next class, while your spinal cord thinks left, right, left, right, left, right, don't fall over, left, right, and so on. We want to hold multiple thoughts at the same time, and those thoughts are carrying out their actions at different time scales. This is something that's often missed in a lot of machine learning and AI attempts, is that intelligence requires being able to do things and orchestrate, coordinate those actions over multiple time scales. Okay, this is one of the more complex experiments we're going to look at in this course. Clearly there's a lot going on, but the idea here is just to sort of show you why we might want to create a continuous time neural network that has, in particular, these tau values, very useful. Okay, any questions about that before we move on? Okay, on to lecture 9. This is one of my favorite lectures in the course. We can think about this as the minimal cognition Olympics. We're going to evolve a bunch of robots to do 4 different events today. They're all very different events, and they all require they all exhibit, robots that are able to do them exhibit 4 very different building blocks of intelligence. Obviously, there aren't just 4 building blocks. There are dozens or hundreds or thousands, depending on how you count. What we're paying attention to is the way these researchers are going to use evolution to bring these building blocks to life in a machine. And then, once they've evolved it, like we just saw now, they're going to look at some of these evolved neural networks and try and figure out how do these evolved neural networks enable the robot to exhibit this particular building block of intelligence. Okay, 4 events today. Let's start with the first one. All 4 of these events are being drawn from the reading for today, which is the actual research paper itself. At this point in the course, we're kind of going to switch over from our reading from the textbook to the actual research papers themselves. For those of you that haven't read many research papers before, this is a good way to get in the habit of reading the primary source. What I suggest you do in all the readings as we move forward, read the beginning and the end first. So if you go and have a look at this paper, there'll be a 1-paragraph abstract that describes what they wanted to do and how they did it and what they found out when they did, which is more or less what we're going to talk about today. The end is going to talk about what they saw along the way and what that means to them and future plans. And the future plans or the future directions part of a research paper is very useful because some of you might take those future research directions that these researchers did not carry out, or they did, doesn't matter, and try a smaller version of it for your final project. So as you're thinking about what you want to do for your final project, tuck in the back of your mind these research papers and what was mentioned by the researchers themselves as things they'd like to try next. In this paper, they looked at 4 building blocks of intelligence. I think at the end of this paper, they mention other building blocks, and by now we've already mentioned more building blocks of intelligence. Could you take this minimal cognition approach and apply it to some aspect of thinking that you're interested in? Okay, we'll leave things there. All right, so as promised, event number 1, perceiving affordances. Humans are primarily visual creatures. We look around the world around us and use our eyes to try and figure out or disambiguate friend from foe, food from poison, and so on. Very, very important. When we look at the world around us, how do we make sense of what we see? This is a big issue. It has been a big issue in AI for a long time. We saw this right at the beginning of the course when we talked about the history of AI. We talked about computer vision, recognizing Marilyn Monroe and separating her from the dark background, right? There's an idea in computer vision all along that the way that we do this, the way we recognize Marilyn Monroe or friend from foe and so on, is to obviously parse the visual scene that we do and look at the relative geometry and use the geometry, color, texture, shape, and so on and say, that's Marilyn Monroe, that's food, that's friend, that's foe, and so on. Psychology, starting in the 1970s, said it's not that simple. We are not just paying attention to geometry. Computer vision researchers, meanwhile, in the 70s, 80s, and even up until the 90s, had a very hard time getting computers to see the Marilyn Monroe in the image, and there was a lack of understanding about why that was the case. One reason is that it seems that when we look at the world, it's not just the geometry that we're paying attention to. Imagine I gave you these 5 images here, and I wanted you to train a neural network to recognize all 5 images as a chair, right? Okay. In the old days, computer vision people tried to do this by saying, well, let's tell the computer a little bit about what it should be looking for. Does the object have 4 legs? Does the object have a relatively flat surface above the 4 legs? Does the object look solid enough to act as a chair, and so on? All these sort of geometric properties. As you can see, and I picked these images on purpose, right? Only one of these objects has 4 legs. So, okay, Let's tell the computer it can have 4 legs or maybe 1 leg with some sort of support underneath. That's okay for this one. What is this thing? Now I don't know, right? There's an infinite number of exceptions you can think of if you try to describe a chair geometrically. Very difficult to do. Obviously, geometry is the only thing we have to go on because we're looking at images. What do humans do? What are we doing when we look at these 5 images? Psychologists, starting in the 1970s, said we look at the advertisements or affordances that these objects project back to us. So objects out in the world, when we look at them from our point of view, it seems that these objects are holding up their hand and advertising their use. They advertise how they may be used by the observer, the human observer. So the true definition of a chair is not it has 4 legs or maybe 3 or maybe 1 and a flat seat and so on. It's not a geometric description. It's a functional description. Some of these the objects are chairs if they afford to us the action of sitting. We could sit upon them and it would support our weight. That's the definition. An affordance is an advertisement about function. So when we look at these, we mentally simulate somehow ourselves. We imagine ourselves trying to sit on these objects and mentally running that simulation to see whether it's successful or not. That's an affordance. In order to do that, we're not just looking at the object, but we're thinking about the relationship between ourself and the object. That's perceiving an affordance. We're going to try and teach a robot, or the experimenters here are going to try and teach a robot to do that. So to build up an intuition for the affordance game, here are 5 objects which obviously all share one thing in common. What about these objects? Geometrically very different. What do they all share in common? Those of you that took my HCI class, you've seen this before. They're energy sources for us, right? And obviously the one in the middle here is the same in both cases. Obviously objects project lots of different affordances. A tree stump, from our point of view, has multiple uses. And which particular affordance seems to arise in our consciousness depends on obviously what else is going on, right? If you're very tired, then maybe a tree stump projects the affordance of sitting. If you're very cold, the tree stump may suggest a heat source, right? It depends, gets complicated. Okay, gets complicated. So again, we're going to try and simplify things by looking at our first minimal cognition experiment. In most of these minimal cognition experiments here, we're going to use a very simple simulation. Just 2D, we're going to throw away 3D. We're going to throw away all the physics that exists in PyroSim that you've seen so far. And our robot is going to be this simple square at the bottom. And this robot has 2 motor neurons. And those 2 motor neurons are attached to 2 rockets sitting left and right on the robot. And when the motor neuron fires and fires up that rocket will push the robot in the other direction. And if both rockets are firing, depending on their strength, the robot will move backward and forward along the bottom of the screen. So this is Space Invaders evolutionary robotics style. All right? So 2 motors, 2 rockets so far. I haven't talked about the sensors yet. We'll talk about them in a moment. In the case of this first experiment, we have our robot that's able to move left and right along the bottom of the screen. As it's doing so, pairs of square objects are going to start to fall from the top of the screen down towards the robot. And in this particular task, we want the robot to try and move between the gap in the pairs of objects if the gap is wide enough for the robot to get through. In this experiment, you are now perceiving affordances, but not for yourself. You want to try and infer the affordance projected by this pair of objects relative to the robot. Can the robot thread the gap here? Can it get between this pair of objects? No, it's too narrow. So in this case, the robot should move out of the way. It should run away from this pair of objects. First of all, it should perceive the fact that it cannot thread the needle. It cannot get through this gap and then head in the other direction. If, however, a pair of objects fall in which the distance between them is wider than the width of the robot should move towards them and allow the pairs of objects to fall on either side of it. It should go through the aperture. So the robot has to evolve the ability to sense the width of that gap relative to itself and decide, quote unquote, decide whether or not to attempt passage between them. Okay, two rockets, and as you can see with these gray beams here, the robot is equipped with 7 ray sensors or distance sensors emanating from its front. And at every time step, it's getting back 7 floating point values that represent the length of these beams. So the robot knows the distance of its ray sensors at every time step. It knows nothing about blocks and distances between pairs of blocks. The neural network is going to have to infer that information from the 7 values at the current time step, and possibly, if the neural network inside this robot, through recurrent connections, what were the values of these 7 sensors at the previous time step. So far, so good? Okay, inside this simple robot, and all the robots we're going to see in this lecture, there are C tier and Ns, and the experimenters are going to evolve all the or they're going to allow evolution to evolve all the tals, all the Ws, all the Gs, and all the thetas. We're not setting anything by hand in these experiments. Okay, we then need to come up with a fitness function that's going to select for robots that perceive affordances correctly and penalize robots that do not perceive affordances correctly. For each single C tier and N that we're going to attempt on the robot, we're going to try it num trials times. Let's zoom in a little bit here. We're going to try out each robot, each C tier and N, a number of trials. It's not specified here. We're going to try it multiple times with multiple pairs of falling objects. So we want to see how well this robot does, not just with a single pair, but on average. We're dividing by the number of trials. On average, how is its performance at this task? So P sub I is going to be a single number, which represents how well a particular C tier and N did when exposed to a particular pair of falling objects. Okay, there are 2 conditions here. We might drop a pair of objects in which the opening is too narrow for the robot to pass between. Let's start with that. If the aperture is too narrow, we're going to assign a performance value of 100 if the agent does not collide with the walls of these pair of objects. Actually, there are no walls here. The robot can move as far to the left or the right as it wants. So if the robot does not hit the pair of objects when they reach the bottom of the ground, 100 points. That's the best you can do. 2 times the absolute value of D sub I if the pair of objects hit the robot. What is D sub I? D sub I is the final horizontal separation between the agent and the center of the pairs of objects. So as the objects are falling, the robot is moving back and forth, and a D sub I of 0 is the robot is directly underneath the pair of objects. Right? What is the worst possible P sub I value that the robot can get if the aperture is too narrow? What's the worst thing it can do, and what's the value of P sub I that it gets if it does that?
If it gets really very tries to go through.
Exactly. If the robot quote unquote tries or attempts or decides, this is all cognitive language, you don't really know what the robot's doing. But if it happens to center itself between the pair of objects when the objects hit it, worst thing you can do. As the robot moves more and more to the left or the right, this is actually a little confusing. We probably don't want to take the absolute value of distance because distance is a positive value. So forget the absolute here, just D sub I. The further away from the center the robot goes, the greater D sub I is, the better. So it may get hit, but as long as it's trying to get to the left or the right of the pair of objects, the better. And if it moves enough to the left or the right that it misses the pair of objects altogether, 100 points. What is this part of the fitness function trying to tell the robot to do?
If the blocks
Get out of the way, and if you get hit, the more out of the way you get, or your descendants get, the better, right? The higher P sub I goes up. Question?
Couldn't that kind of lead to the block never going even close to the objects and just poking it, I guess?
Absolutely. In this case, the robot could just say, I don't care what's falling from the sky, I'm out of here. I'm heading all the way to the right, and gets 100 points. Great. Doesn't even look at the pair of objects. That's fine as long as the aperture is too narrow. But if the aperture happens to be wide enough that the robot should go through it, then obviously just deciding to run away is not sufficient, right? Remember, we're going to drop multiple pairs of objects for one CTRN. So let's look at the other part of the fitness function now. Now we're going to assume that the aperture is wide enough for the robot to get between. And let's look at the 100 here, right? This is the best thing that the robot can do, which is not collide with the pair of objects and be between the pair of objects when the pair of objects reach the bottom of the screen. The robot is threading the needle. It's getting in that aperture and staying in that aperture as both pair of objects fall on either side of it. It's the best thing you can do. 0, clearly that's going to indicate the worst possible thing the robot can do. This is if, again, the robot does not get hit by the pair of objects and it's beyond the blocks. So if the aperture is wide enough and you run away, that's the worst thing you can do in that condition. Third condition is the aperture is wide enough and one of or both of the objects hit the robot when the pair of objects reaches the ground. Tell me about this term here. It includes D sub I again. Imagine multiple CTRNNs, different CTRNNs. All of those CTRNNs cause the robot to get hit by the object pair when the object is wide enough. But those different CTRNNs cause the robot to hit the pair of blocks at different positions. Some of those hits are going to be better than others. What are better hits and what are worse hits in this case? It's clearly not the best thing you can do. You should be between the blocks, but if you get hit, at least...
The further away you are from the block, like from the center of the block?
From the center, the further you are from the center of the block, so if you just think about the minus D sub I, what does that tell you? What does the minus tell you?
There's a window in which it'll be okay, but that if it's a certain distance away, it's gonna hit the blocks. And so based on where within that certain distance, if it's say just inside or really close to being in the safe zone, then it'll be penalized less than if it's further away from being.
Exactly. It'll be penalized less if it's closer to the center, right? If D sub I is smaller, then we're subtracting a smaller value from 80. So 80 is kind of like, all right, you're hitting the inside edge of one of the object pairs, so you're still not doing great, but at least select for robots that are getting hit at the moment in which their D sub I is less and less. They're getting closer in towards the center of the object pair.
Is this like a fixed fitness function, or is it like you apply the first fitness function if the gap is too small and the second one if the gap is wide?
So that's a good question. So let's have a look at this again. This is our overall fitness function. You can think of, it should probably say P equals here, the summation of P sub I. So we're going to drop multiple pairs, right? And we have all these P sub I's. For some of these pairs, we're going to compute P sub I in this way. And for other pairs, we're going to compute P sub I in this way.
So you're going to have like multiple fitness functions with the same.
If you want to think about it that way, there's one overall fitness function, which is these three equations. So when we say fitness function, that's singular, but there may be subfunctions inside. Yeah? So which of these two is applied depends on which pair of objects are falling. So the fitness function itself does not change over evolutionary time. It's always these three equations together, but which of the second and third equations gets applied depends on what's going on in the robot's environment. It's unlike the gantry robot that we saw last week, in which we evolved for a while with fitness function 1, then changed to fitness function 2, and then changed to fitness function 3. That's a good point. That was a changing fitness function. This is not. So far, so good? Okay, so we've constructed a fitness function which overall is telling the robot, never get hit by the blocks. If the aperture is too narrow, get out of there. If the aperture is wide enough, which you have to figure out, thread the needle, right? So we're trying to train this robot to perceive, to look at the gap. It's going to have to scan the gap and decide, is that gap wide enough for me to get through? Right? It's not just a geometric argument from the point of view of the robot. It's comparing what it senses about these objects to itself. Okay. As you can imagine, this was successful. They trained a robot to do this. And what we're going to look at here, like we just did with our block shaking robot. Yep, question?
If its shape doesn't change, then how do we know it's comparing it to itself?
That's a good question. We don't know how it's comparing it to itself. All we know is that when the aperture is narrow, it runs away, and when it's wide enough, it threads the needle, right? The robot doesn't actually know its own width. It can't see itself. It just has these 7 beam sensors that are going out into the environment. It's inferring that from the fitness function. It's not actually looking at itself and saying, I'm 3 centimeters wide, the aperture is 3.1.
Really judging from the distance.
From the distance sensors, that's all it has, right? Remember also that these objects are falling, so that the values of the ray sensors, as the ray sensors sweep the underside of this object pair, those values themselves are changing. They're probably decreasing. So the robot really never sort of takes a snapshot of the situation. It's some relationship in the neural network between what it senses and its own movement.
It could be kind of interesting if you had a robot that could like extend part of itself, and then if it could like realize what state it's in and then change like what it does depending on that.
Absolutely. We could definitely make this more complicated and more challenging, and that's the point. We want to find this minimal situation in which we start to see the beginnings of the perception of affordances. And then it feels like we do it in a much more complex way, right? If you got your parka on and your backpack and you're trying to get through a narrow door, you might think about it differently than if you're in t-shirt and shorts, right? Our bodies, quote unquote, change, and our perceptions of affordances depend on how our bodies themselves are changing. Could a robot do the same thing? Yeah, nice observation. Okay, so let's take, again, like we just saw, let's take the best evolved neural network and drop it back in the robot many, many times and look at the mean performance of this one neural network. Okay, they dropped the network back in the robot, they took the object pair back to the top, and they dropped it many, many times with relative aperture width being smaller than the width of the robot, negative numbers, or the aperture being positive numbers, wider than the width of the robot. They did this many times, and each dot here corresponds to the average behavior of the robot given that aperture width. They dropped that object pair from different horizontal positions at the top of the screen, but still an aperture width of 0.1 units wider than the robot. And the vertical position of this dot represents the mean final horizontal position of the robot. This is d sub I, right? So where was the robot horizontally relative to the object pair when the object pair hit the ground? Let's look at this particular dot here. Tell me about the robot's mean performance when the aperture width was just a little bit wider than the robot. What did it tend to do?
Looks like some of the times it was way too far away, but some of the times it was close enough, but the error was huge on that.
Exactly. So this band here represents the error bars. This is the mean here. So it means that there's a wide variation in performance of the robot. Sometimes it ran away, and the final horizontal position was up here. It was 40 units either to the left or to the right of the object pair. We don't know, but it was far. And sometimes down here, its final horizontal position was 0. It tried to thread the gap. Was this a good thing for the robot to do? It was wider. It should have always tried to thread the needle. Right?
It's probably a result of like loss minimization because its sensors aren't fine-tuned enough to recognize the difference between that or the dot right before it where it isn't wide enough.
Possibly, right? This robot's a little bit conservative, right? It sort of says, it's close, I don't know. I'm going to sort of err on the caution of sort of running away most of the time. Right here, let's look at this dot here. This is when the aperture width is exactly the same width of the robot. What did the robot do in this case, on average? It ran away, right? Again, makes sense. That was the right thing to do. As the aperture width got narrower and narrower, the robot always ran away. And when the aperture width was 0.2 units wider than the robot always went for it. Excellent. You'll notice that this isn't right down by 0, so it wasn't always right in the center, but basically this robot was, generally speaking, always doing the right thing, with the exception of here. Might have, depending on the quality of its sensors, it may have been able to do a little bit better. Evolution may not always give us the optimal solution, but this is pretty good. And we prefer that the robot is overly conservative, maybe, than overly aggressive. If you don't know, run away, try and be safe. Err on the side of caution. Okay, let's continue analysis of the exact same evolved neural network. Let's try and dive down in a little bit more detail and try and figure out how this neural network allows the robot to perceive affordances. Okay, here we go. Let's start at the top of this picture here. The top of the picture here, as you can see, each line here is going to correspond to a pair of objects being dropped to at the very left of the screen, near the center of the screen, and at the top right of the screen. Okay, so we're going to drop the object however many times, we're going to drop the object pair however many times this is, and the pair is going to start falling. And as it starts falling, the line starts to drop, representing the vertical position of the pair of objects. So far, so good? Okay. When the lines start to move diagonally here, this represents that the horizontal position of the robot relative to the object pair is changing. Right? So if you look at this picture, every black dot here, if you think about the x and y coordinate of this black dot, the height or the y coordinate of the black dot represents what's the height of the pair of objects at that time. And the x coordinate, the horizontal position of the dot, represents the horizontal distance between the object pair and the robot. So far, so good? Given that information, what can you tell me about this plot? What is the robot doing? It's always moving off to the side. You'll notice that in all these cases, the relative position is either minus 40 or plus 40. The robot always hightails it either to the left or to the right, which is good, what we would expect it to do in this case.
Seems like when it's more in the middle, it moves left and right, kind of. I wonder if that's a part of it figuring out how wide the aperture is.
You'll notice that all these vertical lines are vertical for the first 20 units as the pair of objects start to fall, which means the robot, although the robot can move, does not move. It's sitting still. The moment these lines start to move diagonally, that means the robot starts to move horizontally. The pair of objects never moves horizontally, it just falls straight down. So the robot waits for a while. Why might the robot be waiting?
To gauge falling speed?
Possibly. Other ideas?
Well, it needs to use the sensors to detect the size of the gap.
It needs to use the sensors, and if we back up a little bit, if you might have caught this in this picture, is that these ray sensors, the length of these ray sensors is not infinite. It can't see infinitely into the distance. So it's not clear from the details of this research paper, but my guess is that the robot can't see anything at this point. There's nothing. All 7 ray sensors are reporting back with maximum lengths. As far as the 7 ray sensors say, the robot says, I don't see anything yet. Clearly, at some point, it starts moving, and it's probably the point at which something touches these sensors. When did the robot decide that the aperture was too narrow? And by when, I mean, what was the height of the pair of objects when the robot said, I perceive the affordance. It's not passable.
Either 60 or 40.
Either 60 or 40. Did it wait that late to make the decision? Maybe. Let's look at this one and come back to this idea. In this case, we're going to drop pairs of objects. Again, same single evolved neural network. We're going to drop object pairs again, but in this case, the aperture is wide enough for the robot to pass. What does the robot do in every one of these cases?
Shoots the gap.
Shoots the gap, right? So horizontal position here is 0. So the object pair is still 40 units above the robot, and the robot's right underneath and is no longer moving. It's just waiting for the pair of objects to fall. When does the robot decide either the gap is too narrow or too wide?
I'd say 50 because it seems like the pattern's pretty much the same between the two all the way until that point, and then that's where it changes.
Exactly. So at this point, if we watch the robot in both cases, regardless of whether the gap is too narrow or too wide, the robot does exactly the same thing. And it's seeing the pair of objects, for sure, in this case.
It looks to me like the robot might be, so if the thing is falling like this, kind of zigzagging until it decides whether or not it wants to stay on one side or...
Sometimes it's zigzagging. So if you follow some of these lines, you can see the robot's traveling to the left, then it travels to the right, and then it stops for a little bit, keeps traveling to the right, gets out of the way, and so on, right? So some of these are zigzagging, some of them are not. The robot doesn't always do the same motion pattern in all of these cases.
It seems like at 50 though, the robot's always centered underneath where the gap is, no matter how wide it is. So it's probably determining at a certain point like how far apart they are at 50 from directly underneath it.
Exactly. So at 50, more or less, it's pretty close. Depends on its situation, but it's slightly at different positions underneath the pair of objects. It's obvious. At time 50, the robot's under the pair of objects, and only then does its behavior start to diverge, and it does different things, right? Thank goodness. This one's actually obvious what's going on. Thinking about thinking is not misleading in this case.
My hypothesis is that because using those sensors, it's a complicated problem figuring out how far apart those objects are based on where the robot is and how far away it is, because sensors are radial. It just decides, I'm going to only calculate it when I'm right under it, when it's 50.
Could be the robot, or evolution in this case is lazy and comes up with an easy solution, which is I'm going to get myself under there and I'll wait, and at this moment I will make the determination, right? Maybe we could break this neural network open and try and analyze it in more detail. There are other hypotheses, however, that fit these observations. This neural network has recurrent connections in it. The robot may have already decided, it may have stored internal state in one or more of these hidden neurons about the situation, but that hidden neuron is not influencing the other neurons for a while. It already knows, and it just starts moving later. Hard to say from just this, right? Our bias would say, well, the simplest thing is you don't need to remember, just make the decision at that time, right? That's how we would probably do it. Not necessarily what's happening here. We can't really tell. Let's have a look. Let's look at one more analysis of, again, the same neural network. I love these researchers because they look in very great detail about what these evolved solutions are doing. We're going to take the same evolved neural network, and now we're going to replay that neural network on the robot many, many, many times so that each pixel in this figure represents one trial with the object pair. Okay. Think about any one pixel in this picture, and let's talk about the horizontal and vertical position of that pixel. The horizontal position of the pixel represents the initial horizontal position. So where was the pair of objects at the top of the screen horizontally relative to the robot? So an x value of 0 anywhere along this line means that the pair of objects was directly above the robot. Pixels to the left means the object pair started upper left, and pixels to the right, the object pair was upper right when it started falling. Yeah? Okay. Vertical position of any one pixel represents the relative aperture width. So pixels that are below 0, y equals 0 here, the aperture was too narrow, and any pixels above 0 here represent apertures that were wide enough for the robot to get through. Okay, so every pixel represents a trial, and the grayscale value of the pixel represents what the robot did. The pixel's white, the robot did the right thing for that condition. Gray means mediocre. It hit a pair of objects. Regardless of whether the aperture is too wide or too narrow, don't hit the objects. That's not a great thing to do. And black is poor. That means the robot ran when it should have stayed, or it stayed when it should have ran. If every single pixel, if this image was empty, all pixels were white, that would mean the robot always did the right thing under every single condition, which it's not. So this is not an optimal robot. How does the robot fail?
When it starts out perfectly positioned below the gap, it fails with very high frequency.
Exactly. So this black spike here represents when the object pair is directly above the robot. And even when the aperture is more than twice the width of the robot, all the robot has to do is stay still. It does the wrong thing. It runs away. Odd. What else does this robot do or fail to do? There's still a lot of black and gray unaccounted for in this image. Let's look at the bottom half of this figure. It's all white. What does that tell you? Succeeded every time that it was too narrow, right? So this is our scaredy cat robot. It's pretty conservative, right? Its tendency is to run, all things being equal, which again is maybe a good thing for our autonomous machines to be doing. Be conservative. When there's opportunity to succeed, what does the robot do in the upper half of this figure? Yep.
The robot has a bias of running away, trying to run away.
It has a bias to try and run away. That's right. That's the cost, right? Often you run away when you should have stayed. You can see there's a lot of black down here, which again represents the robot ran when the aperture was just wide enough for it to get through. So, okay, but maybe a good thing to do anyways. There's also these big patches of gray where it's getting hit.
Would this be a result of a badly poorly designed fitness function?
Possibly. So why is the robot still making these errors? This is the best neural network they were able to evolve. Let's come back and think about the black spike in the center here, right? Aperture's wide enough and the pair of objects is falling center screen. The clue is up here. During evolution, these were the horizontal placements of the object pair at the top of the screen. There's one placement that's missing.
It never evolved to deal with the state in the middle.
The robot never saw the pair of objects falling from above, right?
I think it has to move somewhat in order to judge the distance between the two blocks.
Possibly. It may not have to. You can go back and look at the sensor placement. It may have been able to do this if it had ever seen this situation during evolution. It's not clear. So it's not surprising maybe that the robot failed in this condition because it never saw a wide aperture object pair falling directly above. Never saw that during evolution. That was a new experience when we exposed it to this greater number and variety of trials, which is a warning to us, again, as we try and design AI and intelligent machines. When we deploy them out into the world is always changing. There are going to be situations that our robots and machines experience that they never saw during evolution or training or however we train them, right? There's always going to be these residual uncertainties about what a machine is going to do when it comes up against an unseen environment. In this case, luckily the robot maybe did the right thing from our point of view. It ran. It wasn't sure, and it ran. It could have stayed, but it ran.
In the paper, did they comment on that? Did they leave this out on purpose to have it be the sort of the test case that they couldn't?
I don't think they talk about it, and I doubt they did it on purpose, but maybe they did. Okay, for our purposes, it's a good reminder of this cost of training machines and allowing them to operate autonomously. Okay, so that's the first event. We will just introduce the second event, which is now going to be discriminating self and non-self. In the robot we just saw, it never looked at itself, right? It didn't know the width of its own body. This robot does. This robot's a little bit different. This one sits immobile at the bottom center of the screen, and it has an arm and a hand represented by the line in the circle. And now the two motor neurons work together to pull the arm to the left or the right. And as its arm swivels in front of it, the 7 distance sensors emanating from its center, those distance sensors can touch nothing. They can hit the external falling object, or they can hit the robot's own hand. So now every robot is able to see self and non-self. But beginning robots don't know the difference. All the robot knows is the 7 distance values coming back along these 7 ray sensors. We have, in this case, a single object. That object is going to fall from the top of the screen. You can see now it can fall diagonally straight down. It can fall at different velocities. But all of these objects are going to fall and touch this dotted arc here. They're going to get close enough to the robot. As you can probably guess from all this lead up, what the fitness function is going to do is to select for a robot that watches the falling object, and as the falling object comes towards it, it's going to, quote unquote, grab the object. Its hand should be at exactly the same position as the object when the object crosses that dotted arc. Okay, so the robot has to grab the object, but in order to do that, it's going to have to discriminate between self and non-self. Let's have a look at this. Let's have a look at the fitness function. There's a typo in the paper. The paper mentions a max, but it should actually be a minimum. Again, for each neural network, we're going to carry out a number of trials. And we're going to take the average of the robot's performance, and its performance in the ith trial is going to be represented as before with p sub I. We're going to take the minimum between pi over 4 and theta I, where theta I is the difference, or is the angle between where the object hit that dotted arc and where the hand was when it did so. Are we penalizing for theta or rewarding for theta?
Penalizing, right?
We're penalizing, right? We want theta to be as small as possible. You'll notice here there's a 1 minus. So this theta over 4 is a normalization term. We won't worry about that at the moment. This whole term here ranges between 0, when theta sub I is 0, and 1, the worst possible thing you can do, when the object hits front left and your hand is front right, or the object hits front right and your arm is pi over 4 radians in the opposite direction. Okay, we will stop there and see how our robot does at this task on Thursday. We have a quiz due tonight, and I will see you then. Thank you.